Hello guys, welcome to another video. In this one we are going to talk about mathematics, which in many people's mind is boring. But you're gonna have to use it at some point, especially when you wanted to do like game programming, rigging, or basically general technical artist. Those things has to be some barrier you have to go through. But luckily they're not that complicated on the top layer. And the top layer is probably the layer you need to understand to be able to use them anyways. In many programs like Houdini, Unreal Engine, or Unity, there are mathematical libraries and facilities to deal with the calculation for you. You just need to call the corresponding functions. And all you have to know is that what those different mathematical calculation actually does. We're going to talk about some linear algebra to do linear transformation in this case, and we're going to use Houdini to demonstrate that. Okay, so I'm going to go create a geo and then go inside of it and create a line here. Call this guy v1 for vector 1. Okay, and make it flat. Cool. And then Control C, Control V to have a copy. And then I'm going to merge them together. Alright. Just to be able to see them, maybe I can make this one tilt up like 45 degrees. They're both one unit long, so they're basically unit vectors. And let's imagine that this line is vector 1 and this line is vector 2. And because they're all sitting on the origin, that means the coordinate of point 1 is basically v1. And the coordinate of v3, v2 is actually point 3. Right, so let's go ahead and calculate one of the very common calculation, which is dot product. Okay, so this is vex, but you know, it doesn't matter what language you're using programming wise, it's going to be the same math behind them. So all those things are transferable to all other programs. Anyway, so I'm gonna go get the coordinates of point 1 by creating a vector variable. v1 will be equals to point and 0 p and then 1. So this gives me the position attribute of point 1. Okay, now this 0 basically means the first input. Now we're only using the first input, so you know there's no other way. So we're gonna ask again the current geometry, the first input, the position attribute of its point 1 or point 1 here, right? This one's location basically. Again, that's gonna represent vector 1, and then vector v2 will be point, and then I'm gonna say also the first geometry position attribute, the point 3's location. To get the dot product, we can say f at dot will be equals to dot product of and v1 and then v2. Okay, so this will create a float attribute called dot, and its value is the dot product of v1 and v2. And you can see now in the geometry spreadsheet, there is underneath the details a dot attribute, and its value is 0.7. This 0.7 is actually the dot product of v1 and v2 in this case. All right. So let me go ahead and go back to the v1 and change the direction back to flat. And I'm going to go create a transformation so that I can rotate it through the v, rotation z, right? And just to be able to visualize the result, I'm going to go ahead and create a custom attribute to the attribute angle here, and I can call this guy degree or angle between those two vectors basically, and it's ranging from 0 to 360, and accept that. So now I have this angle slider that I can go from 0 to 360 and copy that parameter. I'm going to paste that into the rotation z here. And it's going to be a relative reference, meaning that they're connected basically. So now whatever I do here will basically rotate the vector 1 now. So let's take a look at the result. When the angle is 0, the dot product result is 1. When the angle starts to increase, you can see the value of the dot product is actually decreasing. And keep on going all the way to 90 degrees, the value actually becomes 0. And then go beyond that, you can see the value keeps going down, and it's now negative, and keep on going smaller and smaller. When I reach to 180 degrees, it becomes -1. Now keep on going beyond 180, you can see the values are now starts to recover, right? Starts to go back. And then when it's 270, or in other words, they're perpendicular again, and the value becomes 0 again, just like the value we were having on angle of 90, right? And then you could imagine what's going to happen after that, right? So keep on going from 270, when the angle becomes basically bigger, or in this case smaller, you can see the dot product starts to increase, and all the way back to 1, just as what we started, right? So somehow the angle between those two vectors will determine the dot product, and there's some really interesting relationship. When they're the same direction, dot product is 1. When they're the opposite direction, the dot product is -1. Those two values are the maximum and minimum values, so it's going to be ranging from 1 to -1. And when the value is 90, or when they are perpendicular, so either 90 or 270, the dot product result is 0. Okay, right? So that means when the two vectors are the same, their dot product is 1. When the two vectors are perpendicular, their dot product is 0. When the two vectors are facing away from each other, like 180 degrees away, the dot product will be -1, right? So that's basically the nature of the dot product. But there's more, right? So far we're dealing with unit vectors. So v1 and v2, they're all having a length of 1. And that's when the statement I have earlier is true, right? So it's going to be ranging from 0 to 1. But what this value actually means is actually something more than that. This value, again, when v1 and v2 are unit vectors, this value is actually resembles the cosine value of this angle here, this angle or this value here. And we can prove that by doing a reverse calculation. So if the dot product is the cosine value of the alpha, we should be able to a cosine it to reverse that to get it the actual angle, right? And then because it's radians, so a cosine actually returns an radian value. We need to convert that into degrees. Degrees, right? And then we can pass that into another float at degree attribute. And run that. You can see now we're getting a degree attribute. It's 29. Now take a look at the angle here. It is exactly 29, right? So that means the dot product of those two unit vectors is actually the cosine value of the angle between those two vectors, right? So yeah, that's actually a deeper meaning of the actual value of the dot product, which also gives you the ability to basically calculate the angle between any two vector by basically getting dot product and then a cosine it, and then convert that from radian to degree. So meaning that if you know two vectors, you basically know their angle. All right. Anyway, so but again, that's when they are unit vectors. When they are not unit vectors, let's try that. I'm gonna change that length to 2 for like vector 1 now. And let's take a look at the result. You can see the degree is kind of like wrong, right? And the dot is also ranging. Let's try 0 here. It's ranging from 2 now to -2. Okay, so when the two vectors are not unit vector, or the actual meaning of this dot product is not just the cosine value of the angle, it's the cosine value of the angle times the length of this vector and then times the length of this vector, right? Now of course it's going to be just the cosine alpha if the two vectors are unit vectors, because timing 1 is not changing it, right? So when they are all unit vectors, the cosine is the value of the dot product is actually the cosine alpha. If they're not unit vectors, it's going to be the cosine alpha of this vector, cosine alpha times the length of this vector, and then times the length of this vector. Okay, so because of that nature, if you swap those two inputs, like if you do the reverse dot product, it's going to give you the same result because the cosine is still going to be the same alpha, right? So it doesn't matter which one you pass in first, the result for dot product will always be the same. And again, the actual meaning mathematically of this result of the dot product is going to be the cosine value of the angles between the two vectors times the two lengths of the two vectors. Okay. All right, I think that's basically dot product on its full extent. To use it though, you can use it to compare directions, of course. To dot product, you can if you're not sure if the vector is a unit vector, there is always a normalized function in all packages I have seen before to normalize a vector. You can see we're getting the correct result again, right? Angle 44, right? And the correct dot product result. Okay, so you can always normalize it, and then you can use dot product to calculate, either to compare like if those two vectors are the same direction or they're perpendicular, which is some case you always wanted to try sometimes to evaluate, right? Or to see if they're completely facing away from each other, or more specifically, you can actually get the exact angle by using this. Okay. And also another interesting thing is that you wanted to know how much this vector is branching on this vector, and you can calculate the dot product, right? If you want to know this guy's shadow, maybe on this line, basically the x-axis in this case, you're able to get it by calculating the dot product, and then you basically divide the length here, and then you got this one's branch over here, basically, which is another usage. Okay, but nonetheless, it's all going to be derived from the concept of what dot product is. All right, moving on from there. Right? That's enough of dot product. We're gonna talk about cross product. So this is dot, and then moving down here, I'm gonna do another one called the cross product. Cross product will yield another vector actually, so it's not a float anymore. We can call this vector v3 will be equals to cross product of v1 and v2. Okay, and just to be able to visualize it, we can create a point on the tip of vector 3 by doing add points, adding a point to the geometry, and its location is going to be v3. You can see how we're adding a point over there. Let me change point 1, v1 back to unit vector so it's easier to understand what's going on. All right, now back here again. Don't want to normalize it anymore. Oops, delete that parenthesis also. So let me also connect a line. So we're gonna add a primitive. It's a poly line, and then it's connecting 0 and 4 points. So from point 0 to point 4, basically. Oops. Oh, tap that wrong. Prim, P-R-M. Typo issue here. So now you can see we have a line connected from the origin to vector 3. So basically this line is vector 3, right? Because we're connecting from the origin to there. So vector 3's coordinate is going to be the coordinate of point 4 here. All right, so let's take a look at what happens to this new cross product vector is if we change the angle. Okay, so when angle is 0, point 4 is actually now sitting at the origin. Its value is 0, 0, 0. You can take a look at the points. You can see point 4 is in fact 0, 0, 0. Okay. All right, now keep on going. When the angle becomes bigger, point 4 starts to, or vector 3 starts to have a length. And then when it's like 90 degrees, it's basically exactly at the coordinate of -1 here on the z direction. You can also take a look at the coordinate here. That's exactly there, right? Now go beyond 90. You can see it starts to shrink again, and it goes back to 0 when the vectors are basically flat. And go beyond that, it flips the direction and becomes longer, and becomes the longest again when those two vectors are perpendicular, right? When v1 and v2 are perpendicular, and keep on going, it shrinks to nothing when they are overlapped again. So again, the angle is basically determining the length of this vector, but there's another very interesting thing about this new vector. In case you didn't notice, this vector is always going to be perpendicular to v1 and v2, and this has a very fundamental meaning in 3D mathematics. If you wanted to ever know the normal direction of any face, you could do that. You could get two vectors on that face, and their cross product is basically the normal direction, right? Because this one is always perpendicular to both vectors, meaning that it is perpendicular to the face those two vectors v1 and v2 resides, right? Right. So this is actually the major usage of the cross product. You ever wanted to get a vector that is perpendicular to those two vectors, you can get their cross product. Now, one thing you notice is that this vector has two possible results. One is that it's facing negative direction on the z direction, or it could be facing positive direction. Okay, and that changes when the two vectors angle is basically beyond 180, right? That's when it flips. Okay, so to know the direction of this new vector of the cross product, you can use the right-hand rule. What you do is you point your index finger to v1, and you point your middle finger to v2, and then basically stick up your thumb, and your thumb will be pointing exactly the direction of v3. And you can try that when those two vectors are actually beyond 180. You have to flip your hand so that your thumb is pointing towards the other direction. So you always know using right-hand rule what the direction of this new vector is based on the other two vectors. Okay, so for now what we know is a cross product will give you a vector that is perpendicular to the two vectors you calculate cross product with, right? Its direction is defined by the right-hand rule. And also more importantly, not more importantly, but something to note is that when the two vectors are the same direction or facing away completely, you will not be able to do that. You get a vector that is 0, 0, 0, which doesn't really perpendicular to anything, right? So be aware of that. And also, you see that the length of this vector changes. If you don't care about the length, you can always normalize it to get basically a normalized normal direction, right? But if you do care about this direction here or what it means, mathematically, it actually resembles something really interesting. Let me show you that real quick. So I'm going to add another point to this geometry. It's going to be adding to the position of v1 plus v2. Okay. All right, you can see that's the new point. It's point 5. And then I'm going to add a primitive. And it's going to be also to the first geometry. And this time it's just going to be a closed polygon. And it's based on point 0, point 1, point 5, and then point 3. So 0, 1, 5, 3 in this order. And then I got this parallelogram. And what's interesting about cross product is that the length of this cross product, the vector of this cross product, is actually the area of this parallelogram, which is, basically composed of those two vectors v1 and v2. You flip them to the other side, you got a parallelogram, right? The area of this parallelogram is the length of this vector. Okay, now not that that's important or something, it's just interesting. And how it's actually the meaning is that is beyond most of the people who is not in the math major. And believe me, this is kind of like nerve-wracking if you look at the actual calculation internally. It makes no sense at all. If you look at what's going on, like you have to memorize what number of those different vectors has to be multiplied and added together, and somehow you get another vector, right? But again, there's a little merit to actually understand why it is doing that, because when you're using it, you're basically only have to know what it means, right? What it means, what it means, right? To do cross product, and what do you get by doing this operation? All right, that's cross product. Okay, so let's move on to maybe quaternions. I'm gonna go ahead and create another geo and add that one. Also a line here, and it's a vertical line. And then I'm gonna create a point here, which is positioned 1 unit away from the origin on the x direction. So it's over there. Let me template the line so we can see the line here. Maybe I can make the background dark. Yeah, that's easier to see. All right, so we'll have a point here and we have a line. Okay, I'm gonna go, do I have to merge them? Maybe not. I'm gonna go create an attribute angle here and connect those two to two different input. Okay, and I'm gonna run over points because there's only one point here, so it doesn't matter. And it's easier to get information from the point if we run over a point. Okay, so quaternion is a very complicated mathematical way to represent a rotation. The rotation is represented by this. It's going to represent a certain amount of rotation around an axis. Okay, so that's what quaternion is. And you can create one. Oh, before we do that, we need to know a vector to, or an axis to rotate around. So we can use this one. Let's say this is the axis we wanted to use quaternion to rotate around. What we can say here is that the vector v will be equals to the point attribute. Now, this time, because this is the second input, so I'm going to say 1 here for the second input. The position of point 1, if you take a look at that, that's point 1, right? Okay. So to create a quaternion, what we can do is create a vector 4. A quaternion is actually a 4-dimensional vector here. Okay, and it does require, let me use Q to represent it. It does have to know, again, the axis you want the quaternion to rotate around and the angle, right? So let's do that. Quaternion, and then we're rotating. You have to specify the angle first. We can use a channel to represent that. Degree, I believe. But quaternion actually is based on radians, so we have to convert degree to radians just to be able to get the correct result. And then we need to tell it the vector we're rotating based on, so v here, right? This is going to create a quaternion, and this quaternion resembles this amount of rotation around this axis. Okay, and we can rotate this point here using this quaternion. So what we can do here is we can say at position, which is the point position in this case, uppercase P, will be equals to Q rotate. Right, and then we're rotating the position, right? And we're rotating based on the quaternion, which is Q in this case. Run it. Oops. Oh, I think I passed the argument in the wrong order. Okay. All right. So I can now click on that to create the channel I defined in here called degree. And I can also go ahead and say you are going to be ranging from 1 to 360 again. Accept that. And drag this. You can see how when I change the degree defined here, how this point is actually rotating around our axis. And this line here. So yeah, don't overthink it. Quaternion basically is representing a rotation, and the rotation is this amount of angle around this axis. Okay, And we could verify that also by maybe tilt this guy, this line here again, maybe 45 degrees. Okay. Now go back here to our rotation here. You can see when I drag this, you can see how it's still rotating around this line, right? Even the line is tilting. So yeah, that's basically what quaternion is in a nutshell. Yeah, it is actually invented by a mathematician, and the time it takes to invent this is actually 10 years. So it took the guy 10 years to invent a system like this. I could never know why it takes so long, but the math behind it is also quite interesting. It's using complicated, numbers, and to see why it's doing those things internally is beyond my comprehension. It's like pages and pages of explanation, and uses a bunch of high-level math that I do not understand. Okay, so again, we don't have to understand it, right? All we have to do is being able to know what it means and use it to our advantage. Okay, so when we talk about quaternion, I think there's another thing we can also talk about, which is something called matrices. So matrices is a more broader transformation. It can represent all sorts of transformation you are familiar with, things like translation or movement, rotation, and also scale. Okay, a matrix basically is representing a linear transformation that you can apply to an object to move it, scale it, and rotate it. Okay. Now, because quaternion also represents a rotation, so basically a quaternion can be converted into a matrix. Let's do that actually. If I remember that correctly, we can say matrix, Q matrix, quaternion 2 matrix will be equals to, how do I do that? Q convert, I believe, which convert into a matrix, and we can just pass in the Q. Right. Now instead of rotating it this way, using the as p equals q rotate, after we convert the quaternion into a matrix, we can just basically say the position equals to the position multiplied the matrix, so q to q2 m. Okay, you can see it is going to basically do the same thing. Just like what I said, matrix can represent transformation, including rotation, and it also includes movement and scale. And because quaternion is also representing rotation, so basically those two are convertible. And there's a function to do that here in Houdini, and I believe in other packages there are other ways to convert between quaternion rotation and sometimes XYZ rotation values basically. Right? So matrix is actually more complicated than quaternion when it comes to structure. It's actually a two-dimensional array, and this one in particular, if we put it into the attribute so you can see it, for at matrix b equals to q to m, it's a 4x4 matrix. And take a look at the value here. All those values is part of the matrix we created. There are 16 values which create a 4x4 matrix. Now it's again, the math is kind of like complicated, but if you want to understand matrix, it's easier to, I think it is easier to understand than quaternion actually, but it does require you to be able to visualize the values and what do they mean. They're using unit vectors, and then basically imagining like how unit vector are transformed after the transformation, and then use that to predict how all other points in the space are transformed. That's the basic idea of linear transformation. But you don't have to understand that either. Just know that matrix represent a certain transformation, and that transformation can include movement, rotation, and scale. And if you want to apply that transformation, just multiply any value to that transformation. It's going to transform that value to the transformed position, right? That's what it does. So multiplication is going to be how you apply matrices. And you can multiply matrices together. Maybe we can take a look at another example instead of hook it up with a quaternion. Let me create another geometry here. Okay, and maybe I can create like a grid. Oh, you know what? Let me do something like this. Let's see if I can do that. So I'm gonna add a point, and we can say vector. We can just type in here. I think we can just type in a value, vector value like 1.5, and then 1. There's nothing here. Let me do a whatever. I don't really care. Just maybe an add node here. Okay. Oh, add point. Oh, I don't need to have the P. Sorry, I'm a little tired. So we're basically adding a point to this position. There you can see we're adding a point in a random position. Not quite random, but it's you know, somewhere not uniform. And I'm gonna add another point, and this point will be 0, and then 2, whatever, 9, and then -10. That's another point, and then I'm gonna add another point, 0, another random coordinate, 3, 1, 5. Yeah, those are 3 points, right? We can also give them, store them into variables. So int p1 will be equals to that, int p2 equals to that, and then int p3 equals to that. And then we can add primitive. First input, poly, and then we're going to add it with P1, P2, P3. So we're basically creating a triangle. Yeah. So let's say we have a triangle like this, but because it's tilted in a weird angle, it's hard to, let's say, if I wanted to cut it into multiple pieces, it's hard to cut it because the angle is like weird. So what I want to do here first before I cut it is that I can maybe bring it to the origin and make it just slightly facing the z direction, for example. Right, now the question is, how can I do that? Well, that's when we can use quaternion to apply the transformation to the points. Sorry, not quaternion, the matrices. So we can create a matrix, but to create a matrix we need to know the rotation and movement we want to apply to those different various, you know, points. So let's do that. First of all, the location is easier to get. Vector location will be equals to get the b box center, basically the bounding box center of our point, and that's basically the location. The rotation is actually a little bit more harder because you kind of wanted to know like how much rotation you wanted to get. So let's actually can pull those all together, right? So to get the angle we need to rotate, we need to know where this face is facing and then compare that to the z direction, right? To do that, we need to say, use the things we've been doing before, right? Vector normal direction will be equals to the cross product of any two lines or two vectors that's you know overlapping with the two edges, any two edges. So we can say vector 1 will be maybe p1. Oh, sorry. Yeah, the location of p1 in this case. So point. Oh, cannot do that actually. We can get the location here. Vector p1 position will be equals to point, and then we can say 0, and then p, and then p1. Okay, and then we can do that again for the other 2 points. P2, P3, P2, and then P3. So now we can cross product P1 minus, oh, sorry, P1 position minus P2 position, and then P1 position minus P3 position. Now this should give us the normal direction, right, more or less. Okay, now we can use right hand rule to get it, and I want to go make it facing this way. So if I use my right hand rule, I think it's gonna be actually, yeah, 0, 2, or basically that's 0, 2 is gonna be P3 minus P0, P3 minus P1 actually. That's the first, so P3 minus P1, and then P2 minus P1, right? So if I use that in theory, use the right hand rule, I should get this cross product, this direction that's facing towards the direction of this face, right, the frontal direction. Then we can normalize it. Okay, we're putting everything we have introduced together. Okay, so this is going to be giving us the normal direction of this face. Okay, now the location is there. Right, we can put that on top. So we're calculating this first, and say this is get location offset, get direction. So this is our direction. Our target direction is actually z direction. So the target direction will be equals to basically 0, 0, 1. Right. Now to get the actual rotation we need to go, we can create a vector 3. We can create a quaternion by doing this. So dihedral, and then we're gonna ask, what's the quaternion that will direct me from this guy to this guy? So this will yield a quaternion. Vector 4, right, is a quaternion. It's gonna yield this guy. This is gonna yield me a quaternion that's needed to rotate from this vector to this vector. Okay, and then we can get a matrix. Matrix rotation will be equals to Q convert, and we're converting that. Oh, actually Q rot. This is quaternion rotation. This is matrix rotation. Q rots. Okay. Now this will give us a matrix for the rotation we need to apply, and for the matrix that we need to move. Okay. All we have to do is create a matrix again. Matrix transform will be equals to make transform. Okay. And then we need to know how we're transforming it. So I'm going to say int and the transformation order, or the transformation order. Do we want to do transform first, on rotation first, or scale first? Right, it doesn't matter in this case. So I'm going to say xform. We don't have to pass in int. Xform, transformation first, and then rotation, and then scale. Okay. And for the rotation, don't really care either. So I'm going to say, because this is just for transform, so I guess it doesn't matter. So I'm going to say xform, xyz for the rotation. Those are defined integers. So those are named integers basically. The xform TRS internally is going to trace back to a I guess, hash defined integer. Okay. So they're integers, basically. You can use 0, 1, 2 if you know what they mean, but this is named integer, so it has more meaning in this case. Right, so afterwards, we need to define the translation, rotation, and scale. Translation will be negative position, our location, because we want to go back, right? For the rotation and for the rotation scale, it doesn't matter. We have rotation matrix already, so we don't need to define it here. All right, so rotation will be 0, 0, 0. Scale will be 1, 1. Okay, so that's another matrix. Okay, two matrix. So now we can do for int p equals 0, and p is smaller than number of points of the first input, and then we can increment p here. So now what we can do is we can start to transform it. So we can say vector current location, okay, will be equals to point, all right, 0, and then p, and then the point, oops, lowercase p. That's our iterator here. And then we can say, yeah, let's transform that p location, right? So p, oops, p location will be equals to p location times, we should do transform first, I think. So transform, and then multiplied rotation. Now the order is actually in mathematics, this is calculated first and this is calculated second. But in different programs, those are implemented differently. So sometimes, just to make things easier to understand, they actually reverse that basic mathematic meaning. So maybe this one goes first, right? This is going to be vary from based on the implementation. Okay, and then we can say set point attribute. We're setting the point attribute, position point attribute to the point, and the attribute will be the new p location after the two matrix multiplications. Two matrices multiplied, meaning two different movements, right? One is rotation, one is transform. Translation. Sorry. So why do I keep typing the wrong case? P location, right? Then run it. Nothing, anything. Alright, that's weird. Unless I've done something wrong. That's actually pretty long here. Let me go ahead and see. I'm not having channels, right? No. Okay. I should have tested in the middle because this is getting a little long. So I'm not sure which one I did incorrectly. I think that's because we haven't added the point yet. So those guys has to be on a different wrangle. So let me cut those things out. Create another attribute wrangle here. And put it into the details and run this. Got warnings already. So I'm gonna say 0 and then 1 and then 2, right? Cool. You can see now how our triangle is actually getting repositioned. This was before, right? It's facing, let me put that into like a template, and this is the result. Before it was like there, right? That's before the purple templated one. Now after our complicated mathematics with two matrices, we're now moving this guy back to the origin first, and we're also making facing the z direction exactly, right? Right? How cool is that? Now we can mathematically do those cool things now. Like that's what's actually happening underneath, like in many programs when you do like move it back to the center, things like that. The underneath math is like this, right? And it's going to be really helpful when you wanted to get informations basically about anything. When it comes to transformation, you can use matrices, and they can represent rotation and transform. Now be aware that again matrices are applied in order. So if you wanted to rotate first and then transform, you can see you're gonna get a different result. It's not in the origin anymore because the rotation here, this Q rotation, it's only gonna assume that you're based on the origin to rotate around that. Otherwise, it's hard to like get one, right? This even it's representing that rotation, but it's assuming that it's rotating based on, in this case, those two vectors, another vector that is perpendicular to those two vectors, right? That's how it's rotating. So in that case, you have to do transform first and then rotate, and that's gonna be based on the origin, right? So you have to do transform first and then rotation. And sometimes in the core, the bare bone mathematic, this actually will be multiplied first. Okay, so you have to read it backwards. But here, I think the internal implementation of Houdini is reversing that. So it's easier to see what's going on. All right, so yeah, that's matrices. Seems complicated, but the meaning, whenever you see a matrix, you know that you can multiply it with a position, and the resulting position will be a transform applied. And it can be a rotation, it can be a transform. You can scale it up twice. If I change that to 2 to 2, the result of the triangle is twice as much bigger, right? That's the scale. Okay. All you have to know is that what matrix does, you can multiply it to apply that transformation basically, and you can multiply multiple ones to transform like in different orders, right? And you can also like create matrix in different ways based on basically the library and how it's implemented. All right, so that's matrices. Those kind of things are going to be something you see a whole lot, when you're doing like deeper technical things. And I think it's really worth mentioning to go through those basic mathematics for linear transformation or linear algebra. I highly recommend you to go through some other videos if you have doubts on it. Once you get used to what's going on underneath the hood, you have a lot of power to do crazy things with matrices and quaternions and linear algebra with dot product and cross product. Okay, so yeah, I think that's it for this video. This is actually pretty long. It's 1 hour, but I think this is totally worth going through to talk about technical things, and maybe in the future we can be able to use it in our other tutorials. All right, that's it for Mess of 3D Graphics. Thanks for watching. See you next time.